After understanding the concept of standard interfaces and how does devices work, now let us look into how do we get data to and from these devices. So we have been talking about the simple idea of kind of load store to the device and get the blocks of information in and out of the device. Each byte is transferred via the processor uh, in out in a load store fashion. The advantage of this method is a simple hardware and easy programs to access the device. However, that comes at the cost of processor cycles. So it consumes processor cycles proportional to the data size. It seems a kind of a very dumb idea to repeatedly use an operation such as the load in a loop to acquire data from a certain location and not take advantage of a dedicated hardware to do that for you, right? So this is basically the concept of direct memory access, DMA, which requests a device to transfer data directly to the DRAM through the DMA controller. The processor tells uh, the DMA when to transfer the data and how much to send. And then the processor gets out of the loop and the device gets ahead and transfers the data. While the processor only finds out through an interrupt from the DMA. For example, the disk drive access works on this line. The processor requests a certain number of blocks in a certain location in memory and goes to do other processing. And the DMA controller interrupts when the transfer of data is complete, rather than having to wait till it go to that part of the disk and then load a byte at a time and load it to memory. So you can see how much processor cycles were being wasted in the programmed I/O, right? So the processor asks the DMA controller to transfer data to and from the memory directly. Let's see a sample interaction with the DMA controller. The device driver is directed by the processor to request the disk to transfer the data to the buffer at location X in the DRAM. The device driver then goes ahead and programs the disk, and the DMA controllers saying, okay, these are the blocks that are required, and here is the address of the buffer. You should put the data in, and here are the number of required bytes. The disk controller then initiates the DMA transfer after it moves the head of the disk to the proper place. The disk controller sends each byte to the DMA controller. The data passes through the disk controller and through the DMA controller and into the memory without the processor even being invoked. The disk is doing the transfer automatically by incrementing the buffer address location and decrementing the C counter. C is the amount of bytes requested, and when the transfer is done, C becomes 0. And when C becomes 0, the DMA interrupts the processor to signal it that the transfer of the required data is complete. So the processor has only set up the transfer and started to perform other activities while the data was being transferred, and then can access the data from the DRAM. So the processor just let it go until the DMA interrupts it when the transfer is complete. So this is one of the fastest modes of data transfer that actually existed from a very long time, as the processor resources were very scarce, and requiring the processor to monitor and control the flow of data is a very expensive procedure, right? So far, we have understood the concept and requirements of device drivers that knit together all those devices out there in the market that really requires completely different interfaces based on their transmission speeds, predictable, unpredictable behavior, reliability factors, and a whole range of operational parameters related to how they transfer their data. So let's take a brief look at the kernel structure for the I/O system. The kernel tries to hide all these different structures and ways of interfacing them. So a typical structure of the kernel has a kernel I/O subsystem. that presents a standard set of interfaces to the kernel and to the user as well. So this is a kind of a similar abstraction model that we studied earlier, relating to the computational structures that divided the application load into chunks of processing that actually worked on top of each other with only interfaces to the upper and lower levels. And each level transformed the results or the inputs from the upper layer into something that served as the inputs to the lower levels until the problem could be run on electrons. So we studied that computational model in one of our lectures. Okay. So in that model, we saw that the more you go closer to the hardware into lower levels, the more you need to know about the hardware. If you are working in C++ versus C, then C language is closer to the hardware versus assembly, which is even more close to the hardware. And you need to know a lot about hardware while programming in assembly language, right? Similarly, we have one abstraction model here that has its own requirements of the breakdown of the workload. So the closer you go to the hardware, the more you need to know about the hardware devices and all the background information that we have studied until this point. At the top of the user program level, sitting on the kernel that provides user IO libraries, the studio.h and iostream.h, which provides standard IO operations such as the printf, scanf, and cout and cin system calls. The user only needs to familiarize with the parameters of these functions without knowing much about the hardware and using these high-level system libraries. The user invokes the kernel IO subsystem, which is actually part of the kernel that interfaces the user with the device controller. Kernel IO subsystems are standard interfaces, device independent IO libraries. The kernel IO subsystem interfaces the user with the device controller. The kernel IO subsystem interfaces device controllers through the device drivers, right? So this is the place where the device driver actually fits in. So it is part of the kernel IO subsystem. So you can imagine how much of device hardware you need to know while writing code in the device driver level. Yeah. And finally, this is the actual hardware device. Every one of the device drivers you load that is going to talk to a device has to meet a certain interface criteria so that you can use that device no matter how it works. For example, you might have a SCSI device that talks to a disk drive. You might have a PCI that talks to a disk drive. You have a floppy that talks to a disk drive. You have a USB that talks to a disk drive. A whole range of possibilities, right? In all of those cases, even though every device is very different, you can use a file browse on them. You can use a file browse on your USB, copy something, and go to your disk and paste it on your disk. And that really works. So good device drivers could make a lot of difference in any computer system. And sometimes when you update your drivers, all of a sudden your system starts to work faster, right? As a recap from the last slide, we have the user level libraries. This provides simple interface to the user program to perform input and output operations. For example, the Studio and iostream provided in the C++ libraries. The kernel level modules, this provides device drivers to interact with the device controller and device independent IO modules used by the device driver. So this is basically the part of kernel IO subsystem. And then you have the actual hardware. This layer includes actual hardware and the hardware controller, which interact with the device drivers and makes hardware alive. So just please note, a key concept in the design of IO software is that it should be device independent, where it should be possible to write programs that can access any IO device without having to specify the device in advance. For example, a program that reads a file as input should be able to read a file on a floppy disk, on a hard disk, or on a CD-ROM without having to modify the program for each different device. Okay. So device driver or device specific code in the kernel that interacts directly with the device hardware. Uh, and as we already know that it supports a standard to the operating system, right? The important thing is that from the top, the same kernel iOS system can interact easily with different device drivers. And special device specific configuration is supported with the ioctl system call used in Unix and Linux. It is abbreviation of input output control, and it is a system call for device specific input output operations and other operations which cannot be expressed by regular system calls. It takes a parameter specifying a request code. The effect of a call depends completely on a request code. Request codes are often device specific. Okay. For instance, a CD-ROM device driver can instruct a physical device to eject a disk by providing an ioctl request code to do that. If you go to the main pages of the ioctl system call in Wikipedia, you would notice a broad collection that uses the ioctl system call for performing a wide variety of operations because different ioctl work for different devices. So for example, if you are dealing with a blocking interface, you would require the services of the ioctl to actually change it to a non-blocking interface. So you would first open that device and then you would do an ioctl on that device to turn it into a non-blocking interface. The Microsoft Windows provides a similar function named device IO control in its Win32 API. Device driver has two parts to it. So basically it's the top and bottom half. The top half is the part that interacts with the kernel and it implements a standard set of interfaces that basically look a lot like your system calls, like open, call, close, read, write, ioctl, strategy, etc. So some of these are not things that you give to the user directly, but they are mostly standard interfaces. And the top half is the part that starts the IO operations and then put a process to sleep until the results are completed. So the top half is the part that knows about the process. The bottom half runs at interrupt level and it does not know about a process from a thread. All it's doing is that it only takes notifications that an operation is finished. So the bottom half works at a very simplistic form and it's only running in the interrupt level and has its own stack and all. Okay, so in a more simplistic words, the bottom half basically responds to the top half and signals it when certain IO operations are completed, and the top half then figures out what to do. This is the life cycle of an IO request. The user requests kernel IO subsystem, and in a non-blocking case, if the device has a non-blocking interface, so it is possible that we are never going to go farther than this control block, right? Because as we know that in a non-blocking interface, we can always get back immediately with whatever data we have at hand, and maybe the system needed 100 bytes, but the kernel system returned only 2. So the system might request the kernel again for the remaining bytes, and it is possible that the data has been cached in some way, and it get whatever data is available. However, in the case of a blocking device interface, the kernel IO subsystem might not satisfy the request, and in which case it sends the request down to the device driver. And the top half of the device driver will put that process to sleep and it will start the access going. So it kind of tell the process that since I don't have your data, so we will put you to sleep and we will start moving. And later when the device is done, the data is stored in the device driver buffer, and the bottom half checks the interrupt and signals the top half about some completion of IO. And at that point, the top half takes up the process and determines which IO is completed and transfer data back to the user and returns from the system call. So this is the kind of interaction between the top half and the bottom half of the device drivers. So clearly, if you are writing code for device drivers, you would have to adhere to a set of interfaces. Writing device drivers is a very specialized skill that is out of the scope of these series of lectures. Now, how does the operating system know that the device is ready? So this is ultimately the IO is completed. So how does the OS know that the device is ready? So the operating system has issued a command to the IO device either via a special instruction or by writing to a location in the IO address space. And the operating system needs to be notified when the IO device has completed an operation and when did it encounter an error, or when did it encounter an error. This can be accomplished in two different ways, either through IO interrupt or through polling. Both of the methods have their own pros and cons. The downside of the interrupt-based method is its relative high overhead, whereas the polling method wastes a lot of cycles on watching over infrequent or unpredictable events related to some device. Interrupt are great for working with unpredictable devices, and you never waste time on polling. So in short, if the device uses an interrupt to notify the processor of an event, this type of IO is known as the interrupt driven. And if the device has a status register that the software must periodically check, this type of IO is said to be based on polling method. Actual devices combine both of the worlds. For example, high bandwidth network devices, as we know that the packets are received randomly, as they might take different paths, and depending on the protocol, the network might also resend any lost packet, right? If you were to interrupt on every packet coming in, you would simply overwhelm most processors because there is not enough processing power to handle all the saving and restoring of registers and dealing with the interrupts. So what usually happens is that the first packet causes an interrupt. Once it gets it in an interrupt handler, the other packets are polled until it empties out the network card. And then it re-enables the interrupts and gets back to the non-polling state. So it's a combination of interrupts and polling. To get an interrupt in the first packet and poll for the rest, right? So while polling, you are either using an IO instruction where you use in-out instructions to read or write into the memory, or if you've got a memory map status register, so you are doing a load store operation in that IO space. I hope that you got the basic introduction into some of the requirements of the IO systems that are important to understand if in future you plan to write code for device drivers. We also looked into the different ways how a processor can access the registers on hardware device and how the data actually transfers between the device and the processor. Then we talked about the DMA interface, which is a very fast mode of data transfer. The DMA basically automates the process of transferring data between a device and the processor. The processor has to only initiate the transfer of the data, after which the processor goes to perform other activities and gets out of the loop. The device then gets ahead and transfers the data, and the DMA only interrupts the processor when the transfer is complete. Then we talked about the kernel sub-IO system. that is a very important part of the kernel. So using the kernel sub-IO system, the kernel provides the user a standard interface to talk to different devices while hiding out all the variety of available interfaces from the user. I hope this video was helpful. Thank you.